So, hello everybody. My name is Henry Brown. I'm a member of the engineering dean's team here at Virginia Tech. I'm just going to be kind of hosting things here in the background. Today's information session about the AEDL, Advanced Engineering Design Lab. It's not about me. It's about Dewey, who's the manager for the AEDL, and everyone else who we have here, other panelists who are members of the various design teams that work out of the AEDL. So we'll be going ahead and getting started with a video that will be, it's a 10-minute video, just a tour of the AEDL. You'll be able to see some of the different projects that students are working on. And then after that, we will be able to go into a bit of like a Q&A session and talk more in depth about any of the different teams that you all might be interested in.
Hello, my name is Dewey Spangler, and I am the manager of the Advanced Engineering Design Lab, or the AEDL. This facility is 6,000 square feet of space available to undergraduate students who attend Virginia Tech and the College of Engineering. This is a joint venture between the College of Engineering and the Aerospace and Ocean Engineering departments. This is a one-of-a-kind type venture between two major departments on the Virginia Tech campus. And the idea is to provide students with space similar to what we provide at the Ware Lab. There are 10 teams that are housed in the facility, and teams not only build, design, and test a viable engineered product, but they also attend a competition. So the logistics and the extra burden, the extra time required to get to competition is added on to what they would normally do in an engineering senior design type or independent study type environment. Students that work in the AEDL have to obtain a badge. This badge signifies that they've passed certain safety tests through our Environmental Health and Safety Department. These are online tests and classes that they have to complete. There's additional paperwork and a survey that has to be completed prior to working in the facility. We are a 24/7 facility, but only students with the badge can work here. The Aerospace Department has a lot of their students from their major working here, but we have students from other majors working at the AEDL, so it's not restricted to just to one major. We have students in civil engineering, environmental, industrial, computer science, computer engineering, mechanical engineering, even a mining engineering student or two work here because we have developed land rovers that go to Mars. We develop rockets that are attempting to go into low orbital space and carry significant payloads. They have to design and build these rocket systems, and they have a facility at Ketland Farm, which is several miles off of campus, where they can actually launch the rockets. So if you're a hands-on type person, you like to get your hands dirty, you like to design and build something, see it tested, and actually take it to a competition, compete with other schools, the AEDL is probably the place for you.
Hello, my name is Bob Schoner. I am the assistant manager at Virginia Tech's Advanced Engineering Design Lab. This is a new space that was acquired by Ocean and Aerospace Engineering for student teams to work on projects related to competitions. As you might imagine, space is a hot topic today. As Elon Musk says, there's no doubt about it, rockets are cool. So we have 4 teams working on rockets. We have 2 teams working on Mars rover robots. We have a wind turbine team. We have, there's one other team, a satellite team. They're building payloads to go into a satellite that will be launched into orbit. So we have a pretty basic machine shop here. This is one of our more exciting new acquisitions. This is a filament winder, and what it does is it takes very thin carbon fiber that comes on a spool like this. It's super thin, and it goes through a bath of epoxy. You wind it around, this is a cardboard tube, and I could probably stand on this. It's just incredibly strong and light. So we use this for rocket body tubes. Eventually we'll get to doing nose cones and things like that. Like I said, rocketry space is exciting stuff. There's all kinds of new technologies and exciting discoveries. We are in the Project Bay area of the AEDL, and this is where we have 9 teams located. They have different bays, different equipment for their projects. Lots of good stuff happening here. It gets really busy as we get toward the spring and when competitions are, but there's teams in here doing work on their projects.
Hi, my name is Haley Capilliton, and I'm the project manager for the wind turbine team at Virginia Tech. We compete every year in the Collegiate Wind Competition, where we design, build, and test a small-scale wind turbine. A lot of times, the testing is done to mimic what real industrial-sized turbines see in the field. Our team is composed of a project development team, which plans a 100-megawatt wind farm, and then we have a technical team, which is composed of a mechanical, aerospace, and power systems team, which all work together to build everything from our blades to our hub to our generator to create a fully functioning small-scale wind turbine.
Hello, my name is Eric Williams. I am the mechanical sub-team lead here at Rocksat X. Our program consists of a yearly rotation where we design, build, and then hopefully fly a sounding rocket payload in cooperation with NASA Wallops and the Colorado Space Grant. This is a very nice low-cost option to get time and space. We get up to 150 kilometers at apogee, but we are limited to a relatively small payload space. We have to build our entire payload within the dimensions of this payload deck here, so this is about how big we can get. Our mission this year involves a phased antenna array deployed on a telescopic boom in order to detect the Adsb signals coming off of the transponders of aircraft flying over the eastern United States. The objective is to figure out the angle of arrival of those signals in order to determine where exactly the aircraft is. And the best part about this signal is that within the actual data that we're receiving, there is information about where exactly the transmitting object was. So there's inbuilt checking so we can figure out how well we did with our measurements.
Hi, my name's Danny. I'm the current captain of Rocketry at Virginia Tech. Rocketry at Virginia Tech is a student design team. Each year, we try to build a rocket that can fly to 10,000 feet as accurately as possible, and we compete in Spaceport America Cup. So behind me here, we have this year's rocket. We're going to fly it on a solid motor at our local launch facility, Kentland Farms. We try to develop all the components of our rocket in-house, so everything from electronics, plumbing, to the entire airframe. We all do that ourselves, and it's entirely modular. Another cool thing that we like to do is get our members level 1 certified, so you can see my L1 rocket over there, and I'll be flying that this weekend and hopefully get a certification out of it.
Hi, my name is Joey Bench. I'm a junior in mechanical engineering, and I'm here on the SLI design team. For SLI, we compete in a NASA competition. That's a collegiate nationwide team, and we compete in Huntsville, Alabama. This year's challenge, we are building a rocket. It's about a 9-foot rocket, and it's going to around 4,000 feet altitude. We have a team of about 30 people, and we all work together to make this happen. And some people work on the rocket, and some people also work on the payload, which is a planetary lander. And we descend separately from the vehicle that deploys at 600 feet, and then it lands on the ground and takes a 360-degree photo of the terrain and transmits it 2,000 feet back to a base station.
Hi, my name is Kevin Engel.
And my name is Adam Henson, and we're the current co-presidents of the Orbital Launch Vehicle Team. Orbital Launch Vehicle Team was started a couple of years ago with the goal of being one of the first teams well, the first team to put a payload in low Earth orbit. This is a challenging goal, and so OLBT is a very multidisciplinary team with a variety of students in different majors, from business to physics to several different of the engineering majors. That's a very challenging project, and so there's a lot of steps along the way. And to talk a little bit about those, I'll let Kevin talk about some of our current projects.
Thanks. So currently we are designing and building our Hoki .75 space launch vehicle. It is a two-stage sounding rocket that will launch to space, hopefully this November. And in order to test out some of the key design elements for that vehicle, we designed and built Test Turkey, as you can see here, which is a one-stage rocket that's already flown once successfully, and we're just getting ready to fly it again. And once again, this will just kind of test some of those design elements for Hoki .75 and make sure that we are ready to build that rocket and go to space.
All right, there we go. I really like that presentation because I think it just shows how much is going on at the AEDL.
I'll introduce myself. My name is Dewey Spangler. I am the manager here for the AEDL facility. And if you were at the Wear Lab session yesterday, you may recognize me. I was the presenter for that as well. So I manage both labs. I manage for the College of Engineering. And we have some very bright students today on the panel. They're similar to Wear Lab students because they want to study engineering, but they also want to build while they're designing. And when I was, I won't go into too many old stories, but when I was a student in the 1980s, I was here at Virginia Tech in civil engineering, and we had no opportunities like the folks have today. And I'll tell you, the students put these facilities to good use, and they keep me busy, which I like. They keep me on my toes, and which I also like. And they make this a very rewarding and challenging job. And what I'm going to do today, I think, is similar to what we did for Wear Lab. I'm going to go through each team, and if we have a representative for that team today, I'll ask them to speak for a few minutes about what they're doing and answer some Q&A as we go along. You saw in the video the very interesting projects that we're doing. These are not simple projects. Trying to put robots or trying to put rockets into space, trying to build satellites that go into space, try to build robots that work in the space environment is not an easy task. And there's an old saying from NASA that space is hard, and it is. And we have a lot of folks in the aerospace and ocean engineering department that want to go into related fields. And again, back in my day, the aerospace department was much smaller than it is now. It's a very popular department, and it's a very well-known and highly regarded department. But as the video mentioned, that we have other majors here. And getting back to the philosophy of Joe Ware, he wanted a facility where we have students from multiple majors working together. That's how engineering is really done. When you guys go out into the universe, as they say, out into the real world, you're not going to be working with just aerospace or just ocean or just civil or just mechanical engineers. You're going to be working with a full spectrum of people from different professions. So this gives you the ability to start practicing that. So what I like to do, it looks like we've got a good number of participants tonight on a Friday afternoon, which is encouraging. And what I like to do, I'll share my screen and then talk a little bit about each project and ask that representative to chime in. So again, we've seen some general intro type material. I think everyone can see that. Henry, can you see that?
Yes, I can.
Okay. So I think everybody who is contemplating engineering is getting the idea that this is going to be probably a lot of work, but it's a lot of fun. And these students are dedicated. To see the project actually work is an extremely rewarding experience. So, I'm going to try to look at a PowerPoint and I'm going to look at my list of speakers tonight. I think some of them have already chimed in above and beyond this list, but I'm going to ask, do we have anybody representing Invents Rocketry? Or I'm sorry, 3D. Let's start with 3D printed aircraft team. That is a unique program here at the AEDL in that these students build a craft that actually flies completely using a 3D printer. So what you see there is a student with about a 5-foot wingspan, or 3 students with a 5-foot wingspan aircraft. And so this thing is constructed from multiple builds from a 3D printer. So you have some problems with the structure. You got to think about the material use for the structure to be able to carry the loads, the aerodynamic loads. You got to think about the aerodynamics, the ability to go through the atmosphere and not have too much drag on the vehicle. And the team there is holding a remote controller. They are actually going into the area of autonomy, partial autonomy and full autonomy with their aircraft. So that adds a much thicker level of complexity because now you're having to program the airplane to do something on its own. So anytime you do something autonomously, you're going to be pushing the envelope on the engineering sciences a lot. I know Mars Madness is here, right?
All right. My name is Charlene Castillo. I'm a lead for wheels and materials. So we're actually doing a whole bunch of research on carbon fiber and how to implement carbon fiber into our wheel design. We do everything from scratch, and it's a human-powered rover that we get to race at a NASA competition in Alabama.
All right. Can you tell us a little bit about the competition as to what's involved?
Yeah. So it's linked to the Moon to Mars mission. So we get to design this rover, build it, and then compete it as if we're on Mars terrain to see if it can go up steep slopes, over craters, and just race against a whole bunch of different universities.
We also have a question in the chat here. Will you be able to answer that? It's how hard or easy is it, in your experience, to balance your work with your team with regular schoolwork?
So I will say for our team, we do try to dedicate at least 10 hours of a week to meet with the teams and research and kind of get our project moving forward. It is kind of a lot of time spent, but it is a lot of fun, and you do work with really hardworking people, so it does come out to be worth the final product. So I don't know. If you end up joining a team that you really do like, it won't seem like work at all.
Charlene, I have a question, if I may.
Yeah.
What's the advantage of having a human-powered vehicle compared to one that's under power on the surface of Mars?
Yeah. So I guess since we have a whole bunch of rovers and stuff on Mars, and now we're trying to get people on Mars, it would be kind of more, I don't know. I'm not really sure how to answer that question, to be honest.
Well, I think what I'm leading to is that, if you think about it, a human-powered vehicle is probably lighter in weight than something carrying batteries and with a drivetrain. You have a drivetrain on both vehicles, but imagine the savings in weight in going human-powered. And also, astronauts need exercise, so this is a way to provide that.
Yeah, definitely.
I don't know if you've gone through the calculations yet, or maybe one of your classes, how much money it takes to get a pound of something into low Earth orbit. And I believe that number's around $10,000 a pound just to go to low Earth orbit. And to go to the moon, it's about $500,000 to $1 million a pound, and then it's about $10 million a pound to go to Mars. So if you save 10 pounds on your vehicle, you saved 100. I don't know. Did I do the math right? $100 million on your space vehicle and your space mission. So yeah, there's a strong incentive to do this, and that NASA is pushing this kind of technology. Okay, if there's no questions for Charlene, is that how you say that, Charlene?
Charlene.
Charlene. Oh, I'm sorry, Charlene. We'll move on to the next team, and I do believe we have an orbital launch vehicle team representative. So if that person could chime in.
Yeah. So. Hi, my name is Kevin Engel, and I'm the co-president of Orbital Launch Vehicle Team. And what we're doing right now, so our long-term goal is to design, build, and fly a rocket capable of putting a small CubeSat into low Earth orbit. And so we're kind of taking a baby steps approach to that. What we're doing right now, our midterm goal is to design a 2-stage solid-fueled sounding rocket that will go to space. And before we do that, what we're doing right now in the short term is working on design and build of our test turkey launch vehicle, which is just a subscale vehicle that uses a lot of the same design elements of our space launch vehicle. Test Turkey launched once successfully last November, and we're working on launching it again this semester on a larger motor.
Okay, and great. And this is Kevin, I think, speaking. Okay, Kevin. So you had a successful launch here a few weeks ago. What did you learn from that experience?
Yeah, so you know, one thing that we really have been learning a lot throughout this whole process is you know, you really can't have any substitute for subscale testing or just physical testing of components. We do have a lot of really smart people working on you know, computational fluid dynamics analyses, you know, flight profile analyses, and that's great. And those give us a great starting point and you know, drive the design in some ways. But when you actually go out and test your design and see it fly, even if it is successful, which it was, you know, we still learned a lot of things that we could improve upon that you just can't get from a computer simulation. So taking that approach of you know, going slow, taking the time to get things done correctly, and being safe is really helping us out right now.
What level of student are you, or what year are you in school?
Yeah, so I'm actually not even an engineering student. I'm a physics major, and I am a senior. And yeah, I just got involved with OLVT when I was a freshman, and you know, just something that was really fun and exciting that ended up putting a lot of time into, and we've grown a lot as a team since then. So looking forward to seeing where we go in the future.
Great, Kevin. And by the way, Kevin just completed his L2 rocket certification, which, how does that differ between L1? L1 is introductory.
Right, yeah. So another thing we really emphasize on OLVT is giving all the individual students that we bring onto the team experience building and launching their own rockets. So we actually will provide you with a kit that you can build and a motor that you can put into your rocket. And you will launch that to get a EEE Level 1 certification. So EEE is just the high power rocketry organization that manages all the legal aspects of launching with the high power motors and getting people certified to launch on bigger motors. Level 1 cert allows you to launch with like a H and an I impulse motor. And then a Level 2 certification allows you to launch with a I think J through L impulse. So basically the higher certification you have, the larger motors you can use, the more complex vehicles you're launching, and the more you learn about the concepts of rocketry.
Okay, and students can, all students on, as far as I know, all the teams at the AEDL can have access at least to L1 certification.
That is
Kevin,
correct.
thank you. We're going to move on, and I'm going to just take a quick look and see if we have a rocketry VT person. We do.
We have a question real quick. Sorry. For Kevin.
Yeah, sure. Go ahead.
So the question is specifically for Kevin. Are there any ideas for what you want the payload to do once it's in orbit?
No, we haven't really thought that far ahead right now. You know, orbit is really so I guess this is a long answer that I'll kind of spin down into a short one. There's a lot of things like Dewey said, space is hard, right? And so there's a lot of things that go into designing even the smaller launch vehicles. So what we're doing right now is really just focusing on making sure everything works on a small scale before we scale up, and making sure that everything is safe. As far as the payload would be, what the payload would be, we don't know. I guess at this point, like, we're just that's kind of a long-term goal. And when that approaches and when we are ready to undertake that challenge, we'll start thinking about that a little bit more.
Okay, great. Okay, Henry, can we move on to the next team?
Yes, for sure.
Okay, thank you, Kevin. And Rocketry at VT, we do have some representatives for that program. Go ahead, guys.
So my name's Danny. I'm a senior studying aerospace, and I'm the current captain of rocketry.
And I'm Hannah Cruz. I'm a sophomore in aerospace engineering, and I'm currently a member of the structures team on rocketry at Virginia Tech.
So rocketry at VT is an undergraduate team. We're a lot like all the other rocket teams. Our goal, though, is to go to a competition out in New Mexico each summer called Spaceport America Cup. At that competition, we're aiming to hit a certain altitude target as accurately as possible. So this year, we're trying to aim to hit 10,000 feet as accurately as possible, and we're going to do a test launch ourselves at the local launch site, Kentland Farms, at the end of April. And so we'll probably get about 7,000 feet and be able to verify different components of our vehicle. We also participate in a payload challenge. So I have the structure of our payload right here. Essentially, once we get to our apogee, our highest altitude, we're going to shoot this out of our rocket, and we're going to try and conduct an experiment in it to see if we can land it back wherever we decide. So we do a lot of interesting things. We have a lot of different teams within our team that allow students to explore different disciplines like electronics or computational fluid dynamics, like Kevin was mentioning, finite element analysis, building structures, all that stuff is all encompassed in our team as well.
Very good. And you mentioned computational fluid dynamics. We call that CFD for short. That's one thing you'll learn about space technology. There's a lot of acronyms. And of course, CFD is used in aircraft design, and actually Formula Car team at the Wear Lab uses CFD. It's think of it, for the people who are not familiar with that term, think of it as a wind tunnel on the computer. And we have wind tunnels that will determine the aerodynamic forces on a structure or on a vehicle, and then the CFD provides a verification of those wind tunnel findings. Another thing we do a lot is CAD. So I didn't mention this earlier, but working at the AEDL, you'll definitely put your CAD skills to use. So you'll learn CAD, or maybe you learned it in high school. You'll learn it again some in freshman year, and it won't just be forgotten and never used. At the AEDL, you're doing everything on CAD to begin with, and then you're moving over to finite element analysis, which is computer-based stress analysis, and CFD, which is computer-based wind tunnel analysis. So yeah, you're going to put those engineering skills to use. Okay, thanks, guys. Let's move on to the next team. And let me check and see if we have some folks from Rocksat. And we do not. We do. Okay. They must have joined in later. Okay, go ahead, Rocksat.
Yeah. So my name is Nicholas Jones. I'm the project lead for the Rocksat team here at Virginia Tech. Each year we design a payload that will fly aboard a sounding rocket launched out of NASA Wallops Flight Facility. What this looks like is, in the fall, we're mainly focused on the design. In the spring, we're really focused on manufacturing and testing. This year, we were working on developing a Adsb direction finding system. And what that means is there are these signals sent out by planes as they fly, Adsb. And what we're doing is trying to detect those signals from the sounding rocket and be able to determine from what direction they're coming in. Our team involves a variety of majors and skills. We have aerospace engineers, mechanical engineers, ECE, electrical and computer engineering, and a big part of this is focusing on how do we design our payload to survive space. So vibrations, temperature, and the low pressure space environment.
Okay. Are there any questions out there for Nicholas? And you put a satellite. Now, right now, you're putting the satellite on a commercial rocket. And
so we're putting a sounding rocket payload. This is not something that reaches orbit. So we go up to 150 kilometers in apogee, and this is launched out of the NASA Wallops facility.
Yeah. So that's. Have you had success with that in the past, getting a satellite to that altitude? I know that's not easy.
So unfortunately, last year's launch was canceled due to COVID, but we're currently on a clear schedule going forward.
Great. Okay. And I notice you have folding solar panels on your satellite. Is that? Did I get that right? Or
that was last year's payload, where we were developing a deployable CubeSat form factor solar array.
Okay.
You see this picture right here? That's actually one of the solar panels in a TVAC chamber. So
this here.
Thermal vacuum testing.
There's a solar panel right there. Can you guys see my cursor?
We can.
Yes.
Okay. So that's the solar panel. And what is that? What is that chamber again exactly, Nick? Tell us about that.
A thermal vacuum chamber.
Okay.
So it allows us to simulate both the thermal environment in terms of temperature, as well as the low pressure environment. So if we seal this up, this will actually pump out the atmosphere inside the chamber until we get to a low enough pressure that kind of simulates space.
Okay, Eric, and you're with Rocksat. What do you do? What do you do with the team?
I am the mechanical sub-team lead. I'm currently a junior in mechanical engineering, and yeah, we're most of the mechanism and the physical plant to allow the science objectives to be met. So that mostly involves either the deployables if we want to stick something outside, like we have the past couple of years, or and then in addition, brackets for sensor mounting, and then an electronics box in order to keep everything safe. Since this is a sounding rocket, what goes up must come down. So it actually ends up in the Atlantic Ocean where we plan to keep it safe for around 5-ish hours until someone can fish it out.
Well, Erica, if there's no questions in the Q&A, I'd like to ask a question. How is your experience on the Rocksat team helping you with your engineering studies?
Yeah, so I guess the best way that Rocksat has been helping with my education is that it's been giving me practical examples of things that we're studying in class. So and even so we get people in underclassmen all the way up to seniors. We take people with the skills and the drive. So as you continue your engineering education, you learn different things, and then you can apply that to the work that you've been assigned or have taken on. So so just learning how different principles are applied and how they work in the classroom, and then applying them to something that will go to space is a really rewarding experience.
So no regrets for being on the team, it sounds like.
No.
Okay, good.
It's an awesome experience.
Okay, Nick and Eric, thank you so much. You did a great job. Let's move on. I believe, chime in here. Let's see, Mars Ice Challenge. Are you with us today?
Yep.
Okay, all right. Go ahead.
Hey, my name is Ashlok, and I'm the current lead for Mars Ice Challenge. And I think we have the other lead for Mars Ice Challenge as well in our team in the call right now. So what we do is we participate in a competition sponsored by NASA. It's called Moon to Mars Ice and Prospecting Challenge. So the challenge is basically to develop a robot which is supposed to go onto the surface of Mars and drill for ice, water, and minerals, and also give an in-depth analysis of the surfaces we drill through. So we have participated in this competition, I think 3 years now, and we did go to NASA Langley in 2019 as one of the top 10 teams in the nation.
Now, do you have someone else representing Mars Ice?
Yeah.
Would they like to speak?
Yeah.
Yeah. Hello, I'm Anthony. I'm also a co-president of Martian Subsurface Analysis Team, and like Shok said, we participate in this NASA challenge. I am an electrical engineer in my junior year, and I mainly participate in, besides being a lead of the team, I participate in the power electronics behind the whole entire system.
Now, you're an electrical engineering student, and
Yes.
Is this going towards senior design, or are you doing this as an independent study or volunteer?
Well, as of right now, I'm not a senior, so we haven't gotten it to the ECE design team yet, but we are in the process of doing so.
Okay, so this may turn into a senior design project.
Yes.
Yes.
Well, that's great. And, again, you're asking, maybe some of the participants or the guests are asking, why do we want to mine ice on the surface of Mars? Can you guys help me with that one?
For sure. So we wanna. So when we suppose we do a manned mission to Mars or Moon or wherever, so it's gonna be a long mission. It's not gonna be like Apollo 11, which is like a few days or a few hours and we get back. So it's gonna be a long mission. And what we mainly want to do is when we go to Mars or Moon, we want to use the resources present on Mars and Moon. So we want to drill for minerals, water, and ice, so that we can probably use that for use the water for propulsion, for drinking, or many other uses that we might need on Moon or Mars.
Okay, that's great. I want to make sure everybody gets to speak, and our time is running out fast. And I believe if I did this right. We've covered everyone here. Is anybody else here that I've left out? Please let me know.
Hi, I'm here from the wind turbine team.
Which team?
The wind turbine team.
Oh, okay. Yes, absolutely.
Yeah,
And
so I guess
what is your name?
Haley Capilton. I'm
Hi,
the
Haley.
project lead for the wind turbine team at Virginia Tech.
Okay.
So yeah, unlike I guess all the other teams, we are not a space-related team. We actually focus on building a small-scale wind turbine. It's about 2 feet tall with a diameter of 45 centimeters. And then we go to the competition every year that's called the Collegiate Wind Competition, where we compete against about 12 other schools. We test our whole system under a series of different tasks like power curve and safety task and durability. So we see how high up our system can actually last in terms of like wind speed. But yeah, we actually have 4 different sub-teams for our team. We have a mechanical sub-team that builds all of the intricate little mechanical systems like our pitch control. We have our PSC team, which stands for Power Systems and Controls. So they're the ones that actually get the electrical energy that we're generating, and they control our pitch control system. And then we have an aerospace team, and they create our blades. So this year we're actually doing something really exciting, and we've changed up the way we're making our blades to use a hand layup method, which is actually similar to what they do in industry. So it's really cool to see that versus our old ones were just 3D printed. It wasn't really interactive for the aero team, but now we're actually getting to get our hands on them and make them. So it's really cool. And then our final team is the siting team, which is actually a lot of business majors and civil majors, and they help us essentially plan a 100 megawatt wind farm. We don't actually build it, but we get all of the information together and the costs and the permitting, that kind of stuff, and you plan a whole 100 megawatt wind farm like you would do in industry.
Okay, yes. Haley, how is this helping you with your study? You said you were mechanical engineering?
Correct. Yeah, so it actually helped me decide what major I wanted to go into. So I joined as a freshman, and I thought I wanted to go into civil coming into college. I got on the team, and I was on the aero team, and I was like, oh, this is cool. And then I realized I just knew I wanted to work with wind turbines, and I talked to a lot of different people on the team because it is such a close-knit team that I eventually landed on mechanical engineering. And I guess similar to what Eric was saying, it definitely gives you a lot of application to the classes you're going to take even before you take them sometimes. So I was learning a ton on the aero team about fluids and kind of thermodynamics type stuff even. And when I got to those classes, I was ahead of some of my peers in knowing the terminology and kind of applications of those classes.
Well, I think, and also it would make your classroom experience even more interesting.
Yeah, exactly.
You can relate to that. What are your job prospects? Have been thinking about what you want to do when you graduate?
Yeah, so I actually last summer interned with GE on a blade design team, which is pretty much what I would like to do. And then I'm interning with them again this summer in a controls position, so doing a lot of testing and controls for their power curves. So yeah, dream job would be working with GE Renewable Energy on their turbine stuff. And I think the best part about our competition is that you actually go and you get to network with people from companies like Vestas, GE, Apex Energy. And they're there essentially looking for students who have this passion for renewable energy. And it's a really good way to kind of get your foot in the door.
Great. Well, Haley, thank you so much for coming out and thanking everyone. I have a couple of questions here, and we do have about the campus tours. We do have campus tours normally, but once we are under the COVID situation, we've been under that for a year now, that both labs, this lab and the wear lab, is under essential personnel only status. So once we get back to normal, we do a lot of tours. So hopefully next year, for you new folks coming in, you'll be at Tech for the next few years. You can get a look at what we're actually talking about here. And again, virtual is okay. It's great. There's nothing like being here and seeing it. You get a lot of good positive energy out of this place. So one other question I had here is what is the application process? That's a good question. And I think someone's typing in some answers here.
No, I just said that where you could answer it live, but maybe a member of a design team could talk about what their application process is like.
Sure,
Absolutely.
Sure, I can go over our application process. So for Mars Ice Challenge, we conduct recruiting, I think, twice a year in each semester. So at the beginning of the semester, we open our recruiting and we send out emails to all the departments of engineering where we want recruits from, and we send them the application form and they apply to us, and then we go through our interviewing process where we get to know you and see if you'd be a good fit for the team or not, and after which you can be a part of the team. But it's not necessary that you need to wait for our email to reach out to us. You can reach out to us at any time. You can look us up at gobblerconnect.com, and you'll find us there. You'll find our contact information there. You can contact us and definitely reach out to us and ask us about what the process is and if you can be a part of the team in the middle of the semester or not.
Yeah, and I'd imagine it's pretty similar for a lot of other teams too. With my experience of people that I know on design teams, if you're passionate about finding a place on a team, then you'll be able to be a part of one. So I'd just like to thank everyone for coming out here tonight, all our panelists. Thank you everybody for taking time out of your busy schedules, and thank you everyone for coming out tonight. It's great to have you all.
Thank you.
Thank you.
Thanks, guys. Thanks, guys. Have a good weekend, everybody.
You too.